Hello everyone, welcome to COMP125. We are going to continue our discussion about the analysis of algorithms, and I'm going to show you two more examples. The first one is binary search. Okay, so binary search algorithm, as the name of the algorithm says, this is going to be a searching algorithm. You have a list of items and you are looking for a target value in that list of items. But there is a specific thing about this algorithm. This algorithm would be only actually applicable over the input list, which is already sorted. So if you have a list of, for example, numbers or a list of names that has been ordered, you can apply this algorithm. And the whole idea of the algorithm is that uh, because your input list of items is already sorted, okay, just assume that you have this list of items. The target value that you are looking for, you can compare it with the middle item. So for example, if you have a list of integer values, just assume that, for example, the middle item is, the target value that you are looking for is something like 15. What you can do is compare 15 with the middle item in your list. So if the item is equal to that middle item, it is possible, right? It is possible that the item is equal to the middle item. If it is equal, so you're lucky you found it. But even if it is not equal to the middle item, you can get some information and execute a faster search, a smarter search. So if the value in the middle is something like 10, something smaller than the target value, it tells me that although I don't know what has been actually stored in the first half, but still I know that they are going to be smaller than 10, right? So I don't need to compare them with this target value, because definitely the target value is supposed to be in the larger side, right? If it is there, maybe it is not, but if it is in the list, it should be on the larger side. Okay, so it will be, you need to actually search it on this side. So it actually tells me that I can safely ignore this part of the list. So if it was actually a smaller, so for example, if the item at the middle of the index was something like, for example, 20, what we would know is that, so if I'm looking for 15, it should be on the smaller side. So in that way, you would ignore the larger side of the list. So, but it doesn't really matter. It doesn't matter if it is a smaller or greater. It actually tells you that either you find the item or you remove half of the list. You just remove half of the list from the searching. You don't need to check that half. Okay, and then you, what's going to actually happen, you would, recursively repeat the same actions. So let me actually just clean up a little bit here. So just assume that the item that you are looking for is 15 and the item at the middle is 20. So in that case, the target item is, the target item is going to be a smaller, right? The target item is going to be in the first half of the list. So again, you do the same action, find the middle item here, compare your value with that middle item. Whatever is, maybe the item is there, maybe you actually just find 15 there. If it is, that's good, you are lucky, just return true. If it is not there, again, you can say that either the value is going to be greater than the target value or smaller. If the middle item is greater than the target value, it means that you have to search on this part. If the middle value is smaller than the target value, you have to search on this part. So it just actually tells, the whole idea is that you constantly remove half of the part of the list that you are searching in. Okay, so the full algorithm has been written here. In your textbook, it actually just explained it in this way, that you have, again, that phone book. You are searching for a name in this phone book. So you know that in the phone book, the names has been sorted in alphabetic order. So they are ordered, right? And if you are looking for a specific name, the best thing is that you just actually open your phone book at the middle, compare that, for example, page, what is the starting name with the name that you are looking for. If it is smaller, you if the target value that you are looking for is smaller than, alphabetically coming before than the middle, so look at the first half and again find the number in the first half. So instead of going to the algorithm line by line, I'm going to show it to you, run it over an example here. Okay, in this algorithm, I have two variables. One of them is called the beginning, that I'm going to show it like as B. The other one is called end. The beginning will be initialized as 1, end will be initialized as n. You can see that in this example, I have 8 items, so n is going to be 8. So this is going to be the actual index 8. This one is going to be 1. So let me actually just put the indexes here, 2, 3, 4, 5, 6, 7, and 8. Okay, the algorithm tells me that you will continue your search until found is no. You see, found is exactly the same flag variable that we have in the sequential search, that you initialize it as no, which means that you haven't found the item yet. And whenever you find it, you will actually change it to yes. So you will continue your search until found is no, or until beginning is smaller than or equal to the variable end. And you see that the variable end has been initialized as n, variable beginning has been initialized as 1. So yes, at the first, all the condition of the loop is true, so we go inside the loop. We will find the middle value, right? Middle value between beginning and end. So look at this example. Between beginning and end, between 1 and 8, the middle value is going to be 4. So middle is going to refer, or m is going to be actually the value 7. What you are doing then is that you compare the value of the name that you are looking for with n index 4, or actually basically this pointer m that is I'm actually referring to 7. So you compare your target value 10 to 7, compare it to 7. What you can see that 10 is greater than 7. Okay, so if 10 is greater than 7, if 10 is equal to 7, you would found it, but unfortunately 10 is not equal to 7. Now what would happen? You compare it. If 10 is greater than 7, you will update the value of beginning to b, so b will be updated to m plus 1. Okay, so basically it is just like b will be no, referring to this index. The value of m is going to be a pointer, right? M is 4, so m plus 1 is going to be 4 plus 1. It is going to be index 5. So b is going to refer to this part. Let me just write it as a new list here, so that you can actually it will be clear that what's going to happen. 10, 12, 14, and 22. So we didn't actually change the position of E. What happened is that the position of B has been changed to 5. So these are the indexes. 1, 2, 3, 4. This was the previous M, right? 5, 6, 7, and 8. Okay, now at the end of the first iteration of the loop, what happened was just the value of, so you can see that this here actually happened, that the value of beginning has been set to m plus 1. So it's just like, the thing is, the middle item was 7, right? It was smaller than 10. So if I'm looking for 10, it should be on the second half of the list. So it is exactly like I am ignoring this part of the list. So this part has been ignored. So basically it's just like exactly this part has been ignored, including M, right? And it is clear the active part of the list that I'm still searching is going to be from the pointer B until the pointer E. Okay? So again, you are going to actually go and check the conditions of the loop. Still, you haven't found the item, and still the value of beginning is less than the value of end, right? So what you do is, again, you find the middle item, middle index between beginning and end. Beginning is 5, end is 8. The middle index between 5 and 8, you can actually just find it using this formula. 5 plus 8, or B plus E divided by 2. And the result is going to be, so it's going to be 13 divided by 2. It's going to be an an odd number. So we can just get the scaling of the result. So this is going to be 6, okay? The result is going to be the index, because you cannot have an index 6.5, right? So just get the scaling. So the middle index now is going to be index 6. So M, the pointer M, is referring to actually 12. What you do here is you compare 10, your target value, you compare 10 with 12. And you can see that 12, unfortunately 12 is not equal to 10. If it was, it would be good, you found it. But it is not equal to the 5. But it is a smaller than, the value at the index M, 12, is greater than the target. So what you do here is you will update E as M minus 1, which actually tells you that, okay, which half of the list you are interested in. You are interested in this half on the left side, right? So it's just like this part of the array will be ignored, and E will be set to M minus 1. So E will be updated to M is 6, E will be updated to 5. 6 minus 1, this is going to be, E is going to be 5. Okay, so let me actually just repeat that array. 1, 4, 5, 7, 10, 12, 14, and 22. Okay, now the variables that I have is both of them, the B and E, both of them are referring to the 5. Okay, so between B and E, what is the middle index? If when both of them are equal, the middle index is going to be 5. It's going to be equal to B or E. So M is also going to refer to 5. So you compare 10 with the value at index 5, which is equal to 10. And that's great, we found it, and you return, and you can actually just see that you will update the value of found to yes, and this loop will stop, and we actually jump out. We will actually just print the target, the phone number, and we just actually finish the loop. So now you can see that although I had 8 items in the list, but how many comparisons I did? If it was sequential search, the number of comparisons that you would need to find this value would be, you need to actually compare it to, let me actually use a different color. You would need your value to compare it with 1, then you need to compare it with 4, 5, 7, and then you find it at 10. So in total, the number of comparisons will be 5 in sequential search. In this example, right? But I just did 3 comparisons, right? You just compare target with 7, then you compared it with 12, then you compared it with 10. So in this algorithm, in this example, I just actually did 3 comparisons. So now think about it in this way. Just think about that even if the item doesn't exist in this list, the sequential search would need to do 8 comparisons, right? Because it needs to actually compare it with all the items in the list. But even if the item doesn't exist in this list, for example, if instead of looking for 10, you were looking for something like 11, okay? Even if you were looking something like 11, at this point, at this actually position that B and E would reach to this index, and the value of the middle item would be M, you compare 11 to 10, right? So in that case, they are not equal. They are not equal. 11 is greater than 10. Then you would update B to B. B would be updated to M plus 1. So B would be updated to 6. And then what would happen? Then if you actually look at the definition, the condition of the loop, the condition of the loop tells you that whenever beginning became greater than end, you will stop. Okay, so you can see that even if the item doesn't exist in the list, this search would just do 3 comparisons, not 8 comparisons. And this is actually the main difference between the sequential search and the binary search. In the sequential search, the number of comparisons that you would do will be log of n. And why this is the case? Because when the number of, okay, let me actually just show you another, let me, add a slide here, and let me show you that what would happen. If, just think about it in this way, if the item doesn't exist, what is the worst case scenario for binary search? One thing before actually discussing about the worst case and best case scenario. The central work in the binary search, just like sequential search, is you are comparing some item with the target item, right? I wanted to know that how many times I need to compare an item with the target item in the binary search. So in the worst case, again, the item will not be in the list. Okay, so this is the worst case is going to be similar. The worst scenario is going to be similar to the worst scenario in the sequential search if the item doesn't exist in the list. So if the item doesn't exist in the list, and assume that the number of items that you are searching for is, let's just call it n, and let's have, for example, like something like 32. Okay, so the very first thing that you do is comparing the item at, B will be 1, E will be 32, M will be something like 16, right? You compare the item with the item 16, so 1 comparisons. Then the item is not equal to that, so for example, just assume that you are going to either search it in this half or this half, doesn't really matter. So let's just assume that you are searching it in this half. So it's just like in this one step, by just 1 comparison, you remove half of the list. So again, it's like the size of your list is going to be 16. Compare your item with the middle item. The middle item is going to be 8, for example, the index 8. So how many comparisons? Another comparison you are going to actually have. So another let me actually just count it. Oh, it doesn't work. So 1 more comparisons. So the middle index is 8, either on the second half or the first half. It doesn't really matter. That's the size, the number of items is important, right? So just again, assume that you are looking for at this part from 1 to 8. The number of items that you are checking now became 8. So you have 32. With 1 comparisons, you actually make it 16. With 1 more comparison, you make it 8. Again, you actually need to find the middle index. It's going to be at index 4. with one comparison, you make the size to be 4. With one more comparison, you make the size of the list will be 2. With one more comparison, you make the size of the list to be 1. With one more comparison, you make the size of the list to be 0. Okay? So how many comparisons you did? You just did 6 comparisons, right? What is 6? 6 is in fact 32 is going to be equal to 2 power 5. And 5, the number of comparisons that you need is going to be that power plus 1. So that's going to be exactly the definition of log. So log of 32 will be 5. Log of 32 in base 2, right? So the number of comparison, it doesn't matter what is n, the number of comparisons that we would need is going to be log of n plus 1. So I can say that the number of comparisons in binary search in the worst case scenario is going to be theta of log of n. You can see that this one can be ignored because just like, the coefficient, we don't care about them and we remove them. I can just write it as theta of log of n. And this is great because binary search is going to be quite fast. It's not going to be even linear. Let me actually show you the diagram here. When the value of n, the number of items is 8, the log of n, the number of comparisons will be 3. When the value of n is 16, the number of comparisons is going to be 4. When the size of your list is 32, the number of comparisons will be 5. When the size is 64, it will be 6. And you can see that the growth ratio of the logarithmic function is going to be very slow. It means that even if you have a very large size of data, how many number of comparisons you would need just log of n number of comparisons, very small number of comparisons. So your algorithm is going to be very fast. This actually figure compares the growth ratio of the linear function comparing to log of n, which is going to be, log of n is going to be way slower. Okay, so the next algorithm that I'm going to discuss here is going to be the pattern matching algorithm. Again, this algorithm is coming from the chapter 2. We have seen the pattern matching algorithm. So the problem was you have a text document and you are searching for a specific pattern in your text document. We wanted to know that we wanted to actually just analyze the best case and the worst case scenario for this algorithm, just like what we did for the previous algorithms. Okay, you have seen the algorithm before, so I'm not going to just go over the details too much, but a general overview about the algorithm. The algorithm was, the main idea was that you would start from the beginning of your text, right? So you would start from the beginning of the search, and you actually needed to have a variable it's just like a pointer that started from the beginning of the document, the whole document. And what you do is that you, from that pointer, you just compare the character which is referred by that pointer, comparing it to the beginning of the pattern, right? Because if you are searching for the pattern, the first character of the pattern should be found first. You will compare it with the first character of the pattern. If it is equal to the first character of the pattern, you would try to match the whole pattern. If it is not equal, you would just actually update the pointer k. So let me actually just give you an example, something like this, that the whole document, the main text that you are searching for is something like this. That, for example, all A. I'm going to actually just discuss the worst case and the best case scenario. That's why I'm preferring it in this way. So, and you have another, the pattern that you are, this is T, that this is the main text, and the pattern that you are searching for is going to be something like, for example, X, Y, Z. Okay, so the counter, the K is going to be set to 1 at first, right here. K has been, let me use a different color. So K has been set to 1. Okay, so what we are doing here is we compare the beginning of the pattern, the first character of the pattern, with the value at the position K, okay, with this one. If it is equal, you would actually, you started matching the whole pattern. But because if it is not equal, this pointer of K will actually keep updating. So you are not iterating over the full pattern here. What you are doing is just updating the value of K. So this example shows the best case that the pattern that we are looking for does not exist in the text. So what's happening here is that the main actually unit of work that will be repeated is just updating the value of K. It just goes updated, go forward, and for each of these characters, it's not going to be equal to the beginning of the pattern. So it's not possible to be a match, right? And you will stop here because after this point, the length of the string that remains is going to be smaller than the length of the length of the pattern. So it's not possible to have the pattern at all. So you would stop at this point, right? So the total number of comparisons that you would need and updating of K is going to be equal to n minus m plus 1, where m is the length of the pattern, n is the number of characters in the string. Okay, so you saw that I just updated the value of K. I did not need to basically match anything because all of these characters were different than the beginning of the pattern. So I never actually started to match the pattern. Okay, so this is the best case, and the best case scenario for us is going to be when the pattern does, the beginning of the pattern is not equal to any character in the text. So the total number of comparisons in this case is going to be in theta of n. Remember, the total number of actually comparisons and updating of the pointer was n minus m plus 1, and I can actually say that this is going to be because usually m is smaller than n, m can be ignored, and this is going to be in theta of n, right? We can actually say that this is going to depend on the length of the string, linearly depend on the length of the string. So let's just actually discuss about the worst case scenario. The worst case scenario would be when all of the pattern that you have except the last character, let me use a different color here, except the last character, all of the pattern is matched everywhere in the text. This is exactly the worst case example, that AAB, all of them, the full pattern except the last one is matched in the input text. So what would happen in that case? So in that case, K was started from here, then you started actually matching because the first character in your pattern has matched to A, right? Then K is going to stop here, then you keep matching the characters, right? The second character here is going to be compared, and yes, it is also matched. Then the last character is going to be compared, and no, it is not equal. So how many actually comparisons you did here? 3 because of this example, but in total you actually had m number of matching, right? M number of comparisons. M is the number of the length of pattern. So I did m number of comparisons while k was still 1. Okay, so m number of comparisons, then k will be updated to 2. So k will be updated here. Again, what you would actually check is that the value at position k is matched to the to the first actually character in the pattern, right? It is matched. So again, what we do is that k will be fixed and you keep matching all of these characters until you reach to the last character, which is not equal. And then how many match you did here? You did m number of matches, right? You check all of the characters in the pattern. So m more number of matching. And then the value of k will be actually updated and go forward. So you can see that by each update of k, you would need to do m number of matchings. So how many times the value of k is just updating? The value of k, just like here, will be started from 1 and go forward until it reaches to n minus m plus 1, right? So this is k is going to update it this many number of time until actually it reaches to here. Okay, so this is going to be this number of time k will be updated, and for each update you need to do m number of matching. So how many number of matchings in total you are going to need? You need to have n minus m plus 1 multiplied by m number of matching. So if you actually just multiply these numbers, you can see that the result is going to be n to m minus m power 2 plus m. This is going to be the total number of matching that you need. Again, because usually the size of m is smaller than the size of n, so we can actually ignore these two parts and say that the total, the number of comparisons and matching that we need is going to depend on n to m or m to n. You can actually just show it as theta of n to m. This is going to be the analysis of your algorithm. I actually keep saying time complexity because this is exactly the name of this, and you will learn about it in higher level courses. So you would excuse me if I just repeatedly use that name, but you haven't seen it in your textbook, so don't be confused. So the best case scenario for the pattern matching was theta of n, and the worst case, it would be actually theta of m multiplied by n. So if the size of m is large, it would be considerable. If the size of m is very small, it will be actually just linear as well. So for example, if m is 3, you can just say that at the end it's going to be linear, but it is good that you keep both of these two terms and say it as theta of m to n. Okay, so this algorithm that we discussed was searching for all the matching of the pattern. Okay, so now you can actually just think about it as an exercise for yourself, that if I update the algorithm so that the algorithm would stop the first time that we find the first matching, does it going to change the best case and the worst case scenario? And if yes, what will be the best case and what will be the worst case? Just think about this as an exercise. Clearly, the best case is going to be different, right? Because the best case will be when the pattern that you are looking is happening at the beginning of the list. So for example, you are looking for A, and your text is something like this, A, B. So when you actually just find it here, you would stop. So you are not going to actually search the full string, the full text. So definitely the best case is going to be different than the best case that we discussed for the current algorithm. Just think about it, that how it's going to change if we only find the first occurrence of the pattern. This current algorithm that we discussed will find all of the matchings. So I'm going to actually just finish this video. This table is going to summarize the analysis of the algorithms, all of the algorithms that we discussed in this chapter, 2 searching algorithms, sequential search and binary search. We saw a sorting algorithm, selection sort. We saw 3 algorithms for data cleanup and a pattern matching algorithm. And it just actually summarizes all of the time complexity, the best case, the worst case, all of the algorithm analysis. And it actually just summarizes the best case, the worst case, and the average case scenario for them. Okay, so this was actually section 3.4, I think. And the last section of this chapter is talking about intractable problems. Some problems actually cannot be solved in polynomial, in the order of the in polynomial order. So when the algorithm can be actually solved in theta of n power k, we usually actually just say that this algorithm is bounded, is polynomially bounded. So can be usually, for example, 2, so it's going to be n or theta of n, or theta of n power 2, like the selection sort that we saw, or theta of n power 3, theta of n power 4. Okay, usually until theta of n power 6 is going to be just useful. Otherwise, if it's more than this, it's not going to be useful. But anyway, for any value of k, if you find the you analyze your algorithm and you find it to be in the order of theta of n power something, we call that algorithm to be polynomially bounded, and we usually actually just call them to be efficient algorithm. But not all of the algorithm can be run in can be executed and can be bounded polynomially. For example, in the problem of finding the Hamiltonian circle, we cannot actually solve this problem in polynomial time. So what is this problem? Just assume that you have a graph. What is a graph? A graph is going to be, just like you are going to have a couple of nodes, and there is going to be some edges that connect these nodes together. So this is going to be a graph. So this is going to be a graph. It's just like you have 5 edges and 4 nodes. This one is a graph. So as you can see, I have, for example, 5 nodes again, and how many edges? You see that it's just have a connection between between some of these actually nodes. Okay, so what is Hamiltonian circuit? Hamiltonian circuit is a path that you started from one node, and it actually check all of the other nodes and exactly once, and it actually comes back to the starting point. So for example, if I have a graph like this, its Hamiltonian circle will be, for example, you started from here, you go here, 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 and here. So you can see that I saw all of if I give some name to this, A, B, C, and D, the path is going to be A, from A go to B, from B go to C, from C go to D, and from D go back to A. So the starting point and the end point are the same, and you just saw each point, each node exactly once, and you saw all of them. Okay, so this is the definition of the Hamiltonian circuit. And the thing is, if I have a general graph, and I wanted to write an algorithm to find the Hamiltonian circuit in a general graph, the algorithm is going to be very time consuming. The algorithm is going to be very slow. Let me actually just tell you that why this is the case. The thing is, the whole idea here is that you need to search between all possible paths that you can have in your graph. So for example, if you have a simple graph like this, if you started from the node A, okay, so where you are going? If I am looking for a Hamiltonian circuit, it's just like I should search all the possible paths, right? So for example, from A, I can go to B, or I can go to C. I should develop all of the paths, right? So it's just like from A, you have two options. You can go to B or you can go to C. All these options has been actually showed you here, that for example, from A, this is not a graph. It is just telling you that how much search I need to do to find the Hamiltonian circle in this graph that I have here. So it's just like from A, I have two options. Either I should go to B or I should go to C. So if I go to B, I have two options, right? I can go to D or I can go back to A. So that's why it's showing you that from B, I have two options. Go to A, go to D. So if I go to D, for example, I have two options. I can go to B or I can go to C. So you can see that I just show all of those possible, paths. So at the end, what you are seeing here is a tree structure that shows all the possible paths. Each of these are going to be from the root to any of these leaf nodes is going to be one possible path that can be a Hamiltonian circle. Maybe it is not, maybe it is, but I have to examine all of these paths that, for example, is it a Hamiltonian circle? No, it is not, because you are actually repeating A and you are not seeing all of them. Is this one a Hamiltonian circle? No, this one again is not, because A has been repeated and you haven't seen all of the nodes. Is this one a Hamiltonian circle? No, this is not, because you are not seeing D. Is this one a Hamiltonian circle? No, it is not. Is this one a Hamiltonian circle? No, because you are seeing B twice and you did not see C. Is this one a Hamiltonian circle? No, this is not. Is this one a Hamiltonian circle? Yes, this is. Okay, so the thing is, you have to search all of these paths in this tree. So to be able to know that how many paths I have in this tree, the idea is that this is a binary tree, right? You can see that at each point I have two options. For here I have two options. For this one I have two options. For this one I have two options. For this one I have two options, 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 and two options. Okay, so in total, the number of actually leaf nodes that I get here is going to be equal to the number of paths, unique paths, starting from here to actually reach to any of these leaf nodes. But because this is a binary actual tree, and the number of leaf nodes that I have here is going to depend on how many levels you are going to down, right? At this point, how many options you had? 1. At this point, how many? 2. At this point, how many? 1, 2, 3, 4. So it's going to be 4. At this point, 8. And at this level, it's going to be 16. So you can see that it's actually just growing exponentially. Just each time it will be multiplied by 2. So when I have a graph with 4 nodes, the number of leaf nodes here is going to be 2 power 4. So now think about it, that if I have a graph with 10 nodes, how many paths I have to examine? 2 power 10 points. So any number of nodes in the graph that I have, I need to search in 2 power n different number of paths to find the Hamiltonian circle. That's why I'm saying that this algorithm is going to be very slow. Why this is slow? Let me actually show you some number. Look at this. This diagram actually just compare 2 power n with n2, these diagrams n and log n. You can see that log n is very slow. It means that the amount of work that you would need to do is very small, comparing to linear, comparing to n power 2, comparing to power n. This diagram doesn't really tell you the whole story because it shows you over the small sizes. If I just increase the, actually, for example, if I just show you a larger, actually, the size. This table, these rows shows the size of n. When the value of n became, for example, 100, if your algorithm works in 2 power n, how much time you think it would take your algorithm to be executed? Yes, you are reading it properly. It is going to take 4 multiplied by 10 power 16 centuries. You are not going to be able to finish to finish this algorithm after this many centuries. So don't even think that you write an algorithm that works in 2 power n, that we call them exponential algorithms. So it's actually just too complicated. The main number is just showing to you here. 2 power n is really this big. This many comparisons, for example, needs to be done. Which even if you can do this many comparisons per second, which is really big, this is 10 milliard comparisons per second. A computer should be very fast to be able to do it. Even with a computer like this, you would need this many years to execute your algorithm. And that is for a small input size like 100. 100 is nothing. I mean, in terms of the input size. Most of the time that the input sizes that we are working on, especially nowadays, it's going to be, in terms of some million. So if you have an algorithm that works in 2 power n, that we call them exponential algorithm, just don't think about that. It doesn't actually really worth even trying that. So that's why, those problems that we cannot solve them in polynomial time, there are some problems like the Hamiltonian cycle that unfortunately there is no good algorithm that we can be sure that always it solves the problem. So those problems are called intractable problem, and the algorithm that we have for them are going to be exponential. So for that case, usually the thing that we can do is creating some algorithm that we call them approximation algorithms. These algorithms are not going to give us the correct answer always, the best answer, but they try to partially solve the problem and find a good answer for you in a polynomial time. So they try to give you an answer which is not the exact answer, but still it is a good answer, and you can actually execute your algorithm in polynomial time. So they are going to be efficient algorithms. They are called approximation algorithms. Okay, so in many cases we need to, if you have an intractable problem and you want to solve it, it's better to use an approximation algorithm than writing an algorithm that finds the exact answer for us. So I'm going to finish this lecture. I have some summary for you that In this chapter, we actually examine different algorithms. We saw how to analyze the efficiency of algorithms, both in terms of time and space. We have seen different algorithms that works in log of n, linear, n square. We have talked about the theta of n. This is and we are saying that, for example, an algorithm works in an order of n, works in an order of n power 2, works in an order of log of n. We have talked about the intractable problems and some problems that we cannot, unfortunately, find a good algorithm for them, like the Hamiltonian circle. So just make sure that you read the textbook properly, carefully, and do the exercises in your textbook. These are actually the best exercises. I tried to post it some more. I was thinking of posting more exercises, and then I actually just look at the exercises at your textbook, and I found them the best exercises that I could actually post. So please make sure that you read them and do them for your actual midterm.